tell you, okay, so we got to here, and yeah, so if you like, these are the equations we're trying to solve, but this is not the best way to approach them, actually. So I'll show. So this is a surface in a. So this is a 5-dimensional space, and you have 3 homogeneous equations. So that's a bit like, you know, a projective surface. You would be used to defining a projective variety in this way, but it's just a slightly different weighting for the homogeneous coordinates. But there's an alternative way to think about the Heron triangles, and this is also due to Schubert. This is in Schubert's little pamphlet. And so, yeah, I kind of took the notation of, so Buchholz and Rathbun, they call these the Schubert parameters. And this is a way, so this is actually, yeah, this is what Schubert did. So thinking about a rational triangle with one, a Heron triangle with one rational median. Oh yeah, so sorry, so I was just saying Buchholz had these 2 parameters, theta and phi, which gave a parameterization of rational triangle with 2 rational medians, and you can kind of see that if you've got A, B, C and the 2 medians, and that's the semi-perimeter, then you can solve for those 2 parameters in terms of, you know, the sides and the medians. So that's just, that was Buchholz's parameterization when K and L are medians, but this doesn't tell you anything about the area, so then you have to compute the area and take a square root, so that's a sort of different thing. So what Schubert did, as I said, he thought about the Heron triangle with one rational median, and then one way to parameterize it, so again it's sort of some elementary trigonometry to see this, but you take here's your median and ABC, and then you take these 3 angles, alpha, beta, gamma. So if you like, alpha and beta are the angles that are created by this bisector that's bisecting the side A, and then there's this other angle gamma at the base, and then you take some parameters M, P, and X, which are half-angle cotangents of those. So take half of those angles and take the cotangents, and then what you can see is that in this case these have to be rational numbers, but they satisfy a relation which is an affine surface now. So you've got M, P, and X satisfy one affine equation. So they're affine coordinates, and they satisfy one equation. So that's in 3D, and then you've just got one affine. So it's an affine variety. It's actually degree 4 because if you is that right? If you yeah, because if you multiply, if you clear the denominator, then for example here you'll get xp m squared and so on. So it's like a quartic surface in 3 dimensions. And now a rational point on this surface, up to maybe, as I said, you might want some conditions about the triangular equality, but basically it's taken into account here. So a rational point on this surface, on this affine surface, corresponds to a Heron triangle with one rational median. And then actually you can see, so a bit like the way I was writing that formula there, if you're given the area and the median k and the side lengths, then you can solve for these Schubert parameters n, p, and x. So again, this is sort of just elementary trigonometry, that you can write those Schubert parameters in terms of the side lengths, the area, and the median. So you can see these formulae just have a, b, c, k, and delta. So that's for just one rational median. And then also another thing you can see is that this is a sort of homogeneous, or weighted homogeneous, because the m's are affine parameters, and remember that the delta and a, b, and k, those are sort of homogeneous because we have scaling freedom. So these ratios are, are inhomogeneous ratios, and then what that tells you is that also the ratios of the side lengths must be given in terms of these affine quantities. So then you can write a over c and b over c in terms of x and p and m. So the formulae to sort of that I'm going to basically work with that I really worked with was essentially this surface equation and these equations for the side lengths. And then now the question is, what if we want to have one of these, but we want to have 2 rational medians? But what that means is that we have to have two rational points on the same surface, but also subject to a pair of constraints, right? So what does that mean? Well, if we've got k is rational and the area is rational, then that gives us a solution of this affine equation. But then if we also have L being rational, then that gives us another triple MPX that satisfies the same affine equation. But then the ratios of the sides also have to be given in terms of the points on that, the 2 points on that surface in two different ways. So then what you get is a total of 4 equations for 6 affine variables, right? So there's 2 copies of the surface equation and then 2 relations coming from these side ratios. And so you can think of that another way of getting a surface, and so now a surface in 6-dimensional affine space. And this is actually what Buchholz and Rathbun looked at in their first paper that they did together. They started looking at the triple, so this is kind of amazing. In fact, I don't think I've shown it here, but it may be on the next slide. I think it's on the next slide. So what they did is they said, okay, we've done a brute force search, we've found these triangles, and then we know the A, B, C, and so on, so we can compute the Schubert parameters. So the Schubert parameters that come from one median and the Schubert parameters that come from the other. So I've labeled them with index A and B because one is the median of side A, the other is the median of side B. And then they looked at what these rational numbers are. Okay. Now I should mention that there's a little bit of freedom, a discrete freedom, which I didn't talk about, which is that there's a freedom to replace, that the surface equation has some symmetries, which comes down to replacing the Schubert parameters by minus their reciprocals. So there's a small group of discrete symmetries, but modulo that group of symmetries, each point is identified on the surface is identified with one of these triangles with one rational median. So what they did is they wrote out, so again, modulo is freedom, so sometimes you'll see a minus sign, and sometimes there's a choice of whether you take this or the reciprocal or minus the reciprocal, so there's a little bit of freedom. But they found a sort of canonical way, they felt, or a good way to write down the side lengths, and they noticed some amazing coincidences. So let me see. If we look in, so let's see if I get it right. Let me look in this one, 18, 6, 7. Oh yeah, okay. So the way that they looked at it, here's the A parameterization, and here's the B. So if you look in this column, and then you look in this column, one row down, you'll see that this one is minus the reciprocal of this one is minus the reciprocal of this one, and that pattern, okay, it doesn't work there, but that's because it's an asterisk, it's an anomaly. But then if we go down to here, you'll see that this one is minus the reciprocal of this one. So they found that they could match up from one row to the next. So if you throw away the sporadic ones, the asterisk ones, then there's some kind of relation between the at least one column and another column in a different row. Okay, but then they did more. So they looked at prime factors of these rational numbers, and they found that there were lots of prime factors which were also moving between, from one row to the next in a pattern. So then they made a kind of crazy, amazing conjecture that actually there was a pair of integer sequences, and they could decide what were the prime factors that would be organized, and they could write these rational quantities in terms of ratios of terms from these two integer sequences. So let me come on to that. Okay, so now I haven't missed anything. So this is a little sort of interlude, intermezzo, I suppose, because it's a different story. So this is kind of something else that I worked on for many years, which is sort of these, well, I mean, mainly I worked in integrable dynamical systems, but in the last few years particularly dynamical systems related to cluster algebras. And I won't try and define cluster algebras because that's like a whole lecture or a whole lecture course if I wanted to do it. But the point is that you have this is a particular sort of quadratic recurrence relation, which is called Somos 5, which was found by Michael Somos, a computer scientist in Ohio who was playing around with lots of recursion relations. And the most general thing you can write down looks like this. I don't really need the most general, but so the structure of this recurrence relation is that you have a product on the left, so you can write that as x new times x old, and then a sum of monomials that depend on other x's, if you like, sort of intermediate variables. And this kind of structure is what's called an exchange relation that comes from a mutation in a cluster algebra. So again, just to sort of give a very broad, sweeping idea of how that works, what you do with a simplest sort of incarnation of cluster algebra, you have a quiver, which is a directed graph, and then you have basically the directed adjacency matrix of the quiver, and that gives you rules for doing what are called mutations. And the mutations are that you pick a vertex on the quiver, and then you do some operations which you reverse all the arrows that are coming in and out of the one that you pick, and then you also add some extra weights which correspond to paths of length 2 passing through the vertex. So it's a sort of complicated combinatorial machinery to describe, but the point is, for this quiver has a very special property, that if you mutate, so mutating at the first vertex, number 1, comes from the exponents that appear in the first row here. So they're 1, minus 1, minus 1, 1. And if you like, the exponents that appear in these monomials are 1, 1, and modulus of minus 1, modulus of minus 1. So these two variables correspond to arrows coming out of the vertex, and these two variables correspond to the variables associated with the two arrows coming in. And so that's where those exponents come from. And that's the mutation that you get from mutating at that vertex. And this process, it produces, so you start with a set of variables attached to the nodes, and then you do a mutation and get a new, so you basically get a new variable at number 1, which is created by this rational formula. But you also do mutation, you also mutate the quiver in the way that I described by changing some arrows. And what's amazing in this particular quiver is that if you mutate at 1, it just rotates the whole quiver does a cyclic permutation of the whole quiver. So what that means is the next step, you can mutate at node 2, and you'll get exactly the same exponent, so exactly the same relation. And for a generic cluster algebra, that's not the case, but this has what's called periodicity, mutation periodicity, which was studied by Fordy and Marsh and Nakanishi and many other people. And so when you do that, then you can actually get a recurrence relation, just a single recurrence relation. And in this case, it's this Somos recurrence relation. But what's remarkable is what's called the Laurent property. And what that means is that under these mutations for cluster algebras, whatever mutation you do, you always get Laurent polynomials in the initial set of variables that you start with integer coefficients. So that's a weird thing. So what it means is, for this recurrence, it means that if we start out with, let's say, so I can put the coefficients alpha and beta, and then we start out with, let's say, x0, x1, x2, x3, x4. So we need 5 initial values to iterate this thing because it's 5th order. Then what we will find is that we know we're going to get rational functions because we have to divide by xn at each step. But what's amazing, the sort of magic of cluster algebras, is that you actually get Laurent polynomials, so polynomials, with just inverse powers of the variables, with integer coefficients. So this is for all n. So then, in particular, if you choose your initial variables to be 5 ones, then you get an integer sequence. So in this case, 2, 3, 5. I don't remember this one. I think 11, 37. Okay, it's on the next slide. But the one that I remember best is Somos 4, but that's a little bit easier. But, okay, there's some other story about. This is a homogeneous recurrence, but actually you can, if you look at the image and the kernel of this skew-symmetric integer matrix, you can find a 3-dimensional kernel which gives you a kind of scaling action, and when you quotient by the scaling action, you get a 2-dimensional affine space, which is actually a symplectic. You actually get a symplectic form out of this 2 form. So what that shows you is when you reduce this map, you actually get this 5-dimensional thing. You get a symplectic map in the plane. So this is what's on the next slide. This is a cluster of 5 variables. You scale it by this scaling just torus, and then so you can replace any variable by xn by b to the power of n, and then a you can scale odd and even indices independently, and then these quantities un are invariants of the scaling action, and then if you reduce everything onto the plane with these affine coordinates, then you find that this is a symplectic form which is invariant under the action of the iteration. And then even more, this is an example of what's called a discrete integrable system, because in fact it has an invariant function. So the way to think about this is think about classical mechanics when you have conservation of energy. So classical mechanics, if you look at just a system with 1 degree of freedom and you have position and momentum, that gives you a vector field, a Hamiltonian vector field in the plane, which conserves energy. And this is like a discrete version of a Hamiltonian system, which has a function which is energy. But then the key to this, to understanding this then, and understanding the solutions of this recurrence relation, is that this quantity, if you fix the value of j, so the level sets of this function, they're cubic curves. So this is an elliptic curve. I mean, generically, for generic alpha, beta, and choice of the constant, this is an elliptic curve. And then, in fact, what you can do, what I did many years ago, you can explicitly solve this recurrence relation in terms of theta functions or elliptic functions. So this is the formula. I use the Weierstrass sigma function on the elliptic curve, on the Weierstrass cubic. Okay, so that's all about integrability, and I'm sort of on track to get there. So this is, this is with the prime factors. So this is what Buchholz and Rathbun were doing with these rational numbers. I've put a kind of degenerate case, which is n equals 0, where you have a collapsed triangle. So this is like a flat triangle, but it fits into the pattern if you include some infinities, a 0, and a flat triangle. So it sort of, if you know what this row is, then that tells you what this part should be, and that fixes the rest. So it's nice to start with n equals 0, and that's because in a way you want to start this recurrence relation with n equals 0. And now, what are this Sn and Tn? Well, this Sn and Tn are particular sequences that satisfy the same recurrence relation, so, but with alpha and beta being 1. So you have Sn plus 5, Sn equals Sn plus 4, Sn plus 1 plus Sn plus 3, Sn plus 2, and the same for Tn, the same recurrence, so with 1, 1, 1 here, but different initial conditions. So there are two sequences that satisfy the same recurrence, but with different initial conditions. And so I have written them down here. So here that is again. So one of them, if I did start off with 5 ones, so I started writing it, and I got up to there, and then I stopped. But we've sort of, this is n equals 0. I've re-indexed it, if you like. This is n equals 0, n equals 1, n equals 2, and then the sequence carries on. And then this one is a bit weird because we started with 0. So obviously 0 is not a good initial value to put into this recurrence relation because you have to divide, and you don't want to divide by 0, but nevertheless this satisfies the recursion with it having a 0 in this place. And these sequences are actually rather special also because they have a sort of symmetry that Sn, you can extend them also to negative indices, and Sn is S of minus n, and Tn is minus T of minus n, so they extend actually all integer n. Okay, so Buchholz and Rathbun, they asked around in the community, sort of in the 90s, does anybody know these sequences? And now there's this beautiful Sloan's online encyclopedia of integer sequences. You can type in your sequence. And Noam Elkies in Harvard, who's an expert on elliptic curves, he said, oh yes, I know this one. This is the sort of original Somos 5 sequence, which comes from this elliptic curve, and I can parameterize it in theta functions. So he gave them a theta function formula, but they weren't really able to do anything with it, so it didn't really help. So they had that beautiful formula on the previous slide for the MP and X, the Schubert parameters, but they couldn't figure out how to prove it. Well, just to say about this curve, if you know about elliptic curves over the rationals, they have they're a finitely generated abelian group. So you have the rank here. The rank is 1. There's just multiples of one infinite order point, and then two torsions. So there's a two torsion point, which is a half period if you want to think about the Jacobian or whatever. And but okay, you can in fact parameterize these sequences with theta functions or sigma functions, and the argument is sort of they look the same formula, but one of them shifted by this half period. But it didn't help them to sort of understand it. But what they did was they looked at their other parameters, theta and phi, that give this other kind of rational parameter formula, for one rational median, and they observed that in the sequence that they found, the theta and phi parameters seem to lie on some curves as well, so also genus 1 curves, but in a family, in a pattern that repeated with period 7. So what they did manage to prove is that for one of these curves, if you have a rational point on this curve, which is just isomorphic to this one, in fact, birationally equivalent, then you'll get a Heron triangle with two rational medians. So they did manage to say, yes, there is this infinite family, but they couldn't really match it up to their other formulae. So yeah, finally what I did was that I played around a lot with their formulae for the Schubert parameters, and I sort of focused on A, B, and C, and K, and later K and L. But actually, the thing that was sort of really useful was not to look at A, B, and C, because they're a little bit complicated. But if you take the semi-perimeter, and then you take S minus A, S minus B, S minus C, then they actually have a simple formula just as from products like this, so homogeneous products. So here you have to take sums and take moduluses. But these things actually have a nice factorization. And then what you can do is actually show that the formula that Buchholz and Rathbun had for these Schubert parameters, that actually embeds this elliptic curve actually analytically. So you can take any complex point on the elliptic curve, embeds in the complex surface, and then you can verify that when you evaluate it at this particular sequence, you get rational points. So what you want. So this is based on some of this technology that comes from integrable systems, from understanding these dynamical systems that are here related to elliptic curves. And then I mentioned there's this period 7 behavior that happens when you look at these other parameters. And it turns out that when you try to write down these formulae naturally, there's sort of some plus or minus signs. And in fact, what it is, what I realized is if I just go back, sorry, one more, go back to here. So this sequence is all positive, but this sequence has some signs, some plus or minus signs. These are a little bit annoying, but in fact, these plus or minus signs in this sequence repeat with period 14. And that's where the period 7 comes from. And the way to visualize it, I think I've got a picture on here. Okay, this is so the curve that is related to that SOMO sequence, the natural curve that appears, is a cubic curve, but it looks like this. So here Vn will be like Sn plus 3, so it's a ratio of these terms of these sequences. And then if you take any two adjacent ratios like this, they lie on this cubic curve, and this curve, the real curve, looks like this. And then what you find is that this sequence, the ratios that come from this positive sequence, they just move around on this compact oval. They just, densely fill this oval, while the terms that come from the one with the signs, they jump around on these non-compact components, real components, in a pattern that repeats with period 7. So it goes like 1, 2, 3, 4, 5, 6, 7, and then that allows you to prove that you look at the ranges of the points on the real curve, and that the dynamics of this map in the plane tells you that you move around on these different components of the curve with period 7, and that fixes the sign pattern. And then that essentially pins down the formula. And then finally, so these are those UNs and VNs, which are the ratios of the terms. And then, okay, there's another sequence which is the ratio of the two SOMO sequences. That also, the Sn divided by Tn, that's this thing Fn. That also lives on another isogenous curve. But anyway, that's a little more complicated story. And finally, if you want to look at the coprimality of these side lengths, you have to look at these sequences modulo prime, and the elliptic curve has bad reduction, so it becomes singular for primes 2, 3, and 17. And so you just have to take care of some bad primes, and then you can show that the side lengths have no common factors, essentially. So this is probably almost, I'm basically done. The last thing I did was to write down the sporadic triangles, the asterisk ones, and wrote down the Schubert parameters. And there are some very nice prime factors in there. So the question is, can you write them as some ratios of other sequences? But I don't know what sequences. So if you're good at, I don't know, experimental maths, or you're good at computer search, then you might be able to find another triangle like this. The problem is that it's already this is I don't know where exactly how Buchholz. I was in touch with Buchholz. He told me we searched up to this size and we didn't find any more. At some point he said, "Oh, I think we found a new one." I said, "Oh, damn! It's one we've already got." So, so if anyone knows a good algorithms for solving for sort of numerical search of maybe someone doing machine learning has got a way to train some kind of AI system to find solutions of Diophantine equations. But really you need more data, so I couldn't get a pattern out of four points essentially. But really it would be good to know if there's more data. And then you might have a hope of actually proving the really hard problem that there are no unicorns. Okay, so that's a good place to stop. Thank you.
Any questions? So in the sequence 1, 2, 3, 4, can you prove that there aren't no unicorns in that sequence?
Yeah, so I didn't do that, but Buchholz and some people that he worked with, yeah, they used some, as I said, like an effective version of faultings, because the equations that you get for the third median, you end up getting an equation for a genus 2 curve, and then you need to bound, you know that there are only finitely many integer points, say or rational points even on a genus 2 curve, and then there's a way, it's Schubert, there's a way to make those bounds effective, because faultings doesn't give you effective bounds, and then you can, then you can just check that within some family there are no integer points or rational points. Yeah. So that's what they have done. Yeah. There may be a simpler way to do it, because they didn't have the parameterization that I have, so there may be a sort of neater way to do it, but I haven't thought about that.
Yes. These 4 sporadic examples, is it known that they're kind of related to each other at all, or is that?
Well, no, it's not known. I mean, that's also what I've just been staring at the prime factors, like there's a 17 down here. Yeah, there's 17 everywhere. Yeah, 17 everywhere, exactly. So, but it's not the same pattern of factors that were in the other sequences. So, maybe there's some other ratios of things which could give these factors, but I haven't managed to figure it out. I've played around with different ways of searching and looking, but yeah, I mean the way that I proved the result was that I took ratios of essentially, you could say ratios of elliptic functions which would satisfy sort of analogues of this kind of curves. So that essentially that fixes this pattern of poles and zeros, and then you can do like residue calculations, and you have to check residues that certain residues cancel. If you want to prove that 2 elliptic functions are equal, you look at the poles. You just need to look at the poles and then check that they agree at one finite value, and that proves that they're the same function. So you're looking at 2 formulae and trying to analyze all the residues at all the poles, essentially. And by doing those residue calculations, the residues also get fixed to be certain numbers, and then that sort of funnels you down to being really, if you like, the curve that's in this picture. I mean, this is one way of writing the curve, one sort of this curve essentially, and then also particular points on the curve and so on. So a particular point, which is the infinite order point, and then the shift by a half period. So that sort of just comes out from this residue and pole calculation. So if there is another pattern or other families, then it must have a different pole structure. I mean, you can sort of do that arithmetically as well. You can think about like a p-adic expansion in a prime, like powers of a prime, and again you can say, I think that for say whatever prime that there'll be like a the order of modulo of that prime will be such and such, and again it's sort of like looking at zeros and poles, equivalent to zeros and poles. But yeah, I haven't found a pattern to fit them into. So yeah, and I mean I can do Python and sort of searches myself. I've done limited searches, but I'm not the sort of expert on computational number theory. So it would be nice to find some. I was just talking to Kate Stang on Tuesday. I was giving another similar different talk there, but actually we were talking about something different. But she's doing lots of computational projects now in number theory. So I haven't explained this one to her yet. So I'd like to go and talk to her again. But yeah.
Yeah. Very very basic question, which is there anything special about medians, or is it just the first case? I mean, could one ask the same question about like lines that trisect the sides?
Yeah. So okay, so that's quite a good question. So one thing is this is the sort of thing that if you have a perfect triangle, then just the requirement about the medians also tells you that the angular bisectors will also have rational lengths as well. So the thing about a perfect triangle is that more or less any features in terms of lengths that you want to look at, once you've fixed the three medians, then basically almost everything else you would like to measure about it will be rational. So that's why it really is a unicorn in the sense that really it's rational in almost every way you can think of. So yeah, you could look at angular bisectors, and I mean there are lots of other Diophantine problems related to just Heron triangles. There are like the congruent numbers and other things. There are lots of and they all seem to be often related to elliptic fibrations, like families of elliptic curves and so on. There are lots of similar problems that. I mean, I suppose another thing you could say is that you've got this homogeneous, this variety and weighted projective space, and you could just say, well, okay, I don't really care about triangles, I just pick any integer coefficients in those quadratic relations. And then you probably could solve these sort of quadric type things or generalized quadric things using maybe these. You could find families as well for those, but it wouldn't have an obvious geometrical interest, but it would be a potential generalization that would be feasible to do, just sort of deforming this one, I suppose. Yeah.
Hi. Actually, first I see you're in the Department of Mathematics, Statistics, and Actuarial Science.
Yes.
I'm probably the only actuary in the room.
Okay. Yeah.
There's let's see, I can't remember if you mentioned during the talk, but in your abstract or somewhere, it says the elliptic curves that the examples 1, 2, 3, 4, 5 come from is a rank 1 elliptic curve.
Yeah, that's right, yeah.
There's another problem in Guy's unsolved problems where it comes down to if there is an example of a certain thing that comes from an elliptic curve of rank 2 or higher.
Yeah.
There's lots of near misses on rank 1 curves.
Okay.
Well, in fact, it comes from not only rank 2, but it'd have to be, really use the rank 2 or higher.
Yeah.
As opposed to just a rank 1 subset.
I mean, I know another example that has rank 2 curves in it, but I mean, so there's I forgot, Shioda and Chizo, it's the two Japanese that classified, Mordell-Weil groups of elliptic surfaces, and so I have a family of maps which are kind of rather like analogous to this sort of Somos 5 and so on, which also come from cluster algebras where you actually get a family of rank 2 curves. So I don't know if it could be related to, I mean, it doesn't come from a Diophantine problem, it comes from more like a dynamical systems problem or an algebraic problem, that like, here's some dynamics which comes from a certain finite root system by deforming a root system, and then you end up with finding again this kind of cluster mutation, but in fact you find another mutation in the same cluster algebra which generates a translation on the same family of elliptic curves essentially. So and then you can prove that, you know, for generic parameter choice, it is actually rank 2. So initially I just tested. Now also there's this LMFDB, the L functions and modular forms database, so you can type in an elliptic curve and it will tell you the rank and like generators. I mean, if it's not too big, but it's got a huge encyclopedia of huge database of curves. So I just took some choices and checked that the rank was 2, and then I have sort of other arguments to prove that it's rank 2. There's maybe more sophisticated arguments to look at the surface and the elliptic surface and show that it's rank 2. But anyway, so yeah, I don't know. I'd be interested to know because that book is, I've got that book of Guy, but it's a sort of book that you just can dip into it randomly, but it's hard to, at least for me, it's hard to read it from cover to cover because it's just a sort of miscellany of different problems, and so even to find the problem that you're interested in is, you know, not trivial. So, but if you can point me to the problem, I'd be happy to look at it.
You can look it up in the index.
Yeah. Okay.
The problem is magic squares of squares.
Oh, magic squares of squares. Okay.
So,
yeah. That's good.
So it's a question of, is there a 3x3 magic square, non-trivial,
Yeah.
or all the entries are perfect squares?
Okay, cool. Yeah, that's a nice problem anyway. Yeah, that's okay.
And anyway, there's...
And nobody knows an answer.
There's some papers by Andrew Bremner, and including one by Bremner, Silverman, and Sinakis, I think it is.
Okay.
That says if there is such a magic square, it doesn't come from a rank 1.
Okay.
Yeah. I have a little, I guess it's a note in Mathematics magazine that shows the relationship between magic squares
and curves.
Squares and
curves.
curves.
Yeah. Okay.
So that's a pretty easy read.
Yeah. Okay. That's okay. Well, I will look that up then when I get home. Thank you.
Sure.
Yeah.
There's no more questions, but thank you again.